In this chapter, we're going to look at exponential growth. Exponential growth means that an item or quantity grows by a constant factor b per unit. And typically this per unit is a time unit. Let's look immediately at some examples. So in example 1, we have a population of rabbits and their number doubles every week. So doubling, this means this growth factor is 2, and the time unit, in which time do they double, do they grow by factor 2? Well, that's a week. So actually 1 week. Example 2, the amount of yeast triples every hour. So think by yourself, what are B and the time unit? Here comes the solution. B is 3 and the time unit is 1 hour. Example 3, we have a population in a country that rises by 3% every year. So how much is the growth factor here? You have to think for a moment for that one. Well, here comes the result. It's 1.03. I'll explain in a moment why. And the time unit is 1 year. Let's look at an example. Let's say the country has 1,000 persons at the beginning. Well, after 1 year, it has increased by 3%. 3% of 1,000 is 30 persons. So there will be 1,030 persons after 1 year. So the factor by which it has grown is the 1,030, the new amount, divided by the original amount, the 1,000, which is 1.03. Okay, next example. Anna learned 30 new English words every week. What is here the result? Think for a moment. And here comes the result. Well, this is not an exponential growth. How do we call this type of growth? This is a linear growth, which means that the quantity grows by a constant amount, not by constant factor per time unit. This means every week there are plus 30 words. Now let us get to example 5. Another time let us look at the rabbits. So let us now make an assumption that is a little bit more realistic than example 1. We assume that the number grows by 20% every week. So what is the growth factor B? Think about it for a moment. Here comes the result. It's 1.2. And the time unit, well, that's still 1 week. And now let's write down the numbers. How many rabbits are there at the end of the week? Well, I'll start with week 0, which means f of 0 is just the number at the beginning. So it's just 100. How many rabbits are there after 1 week? Well, we have the 100 rabbits that are growing by the factor 1.2. So 100 times 1.2, which is 120. Or just formulating it more generally, calling the 100A as the starting amount here. Let's call it A, the starting amount. And we have this factor B, 1.2. So we have actually just A times B. After 2 weeks, well, how many are there now? There are the 120 we had at the end of the first week times 1.2, which is actually the 120 or the original 100 times 1.2. Here, these 120, we got them that way. So times 1.2. So when we rewrite that, we have 100 times 1.2 squared. So actually A, the original amount, times the growth factor squared. How many are there after 3 weeks? Well, I forgot to write down here. That's 144. So after 3 weeks, we'll have the end amount of week 2, 144 times the 1.2. We can replace it back. We have the 144 is 100 times 1.2 squared times 1.2. So what we get is 100 times 1.2 to the power of 3, which is approximately 173. and it is, to be precise, just a times b to the power of 3. Actually, the amount here would be 172.8, so probably the last rabbit is only born to 80%, not yet completely. Well, however we want to look at it, obviously this whole function cannot represent exactly the number of rabbits, because the function itself will not be only integer numbers, but this is just about the model. Now the question is, how many rabbits are there after n weeks? So what is f of n? And just looking at what we found out by now, we said after 1 week we have 100 times 1.2, after 2 weeks 100 times 1.2 to the power of 2, after 3 weeks 100 times 1.2 to the power of 3. So we see it will continue exactly that way, so we get 100 times 1.2 to the power of n. Or in the general case, just this means it's a, the initial amount, times b to the power of n. By the way, that is also true for the first, for the beginning, which means at time point 0. Well, when I insert here for the n0, b to the power of 0 is 1, so I get f of 0 is just a, as written up here. So we have found that the growth function f of t in this example is just 100 times 1.2 to the power of t. Or in general now, we can formulate our growth function. Exponential growth is always a times b to the power of t. And then what is the meaning of a? A means the t is just the time in time units. F of t is the amount of the item or the quantity at time t. A is the initial amount. This means the amount at time 0. So a is just f of 0. And b is the growth factor per time unit. It is important to note the difference between growth factor and growth rate. The growth factor, b, refers to the total amount, while the growth rate, p%, refers to the amount that is being added, or just the part of the total amount that changes. And the relationship between the two these two things, b and p%, well, that's not so difficult. B is just 1 plus the p%, because p% tells me the factor by how much something is added, the factor of the beginning, so I have to add the factor 1 first. So for example, if I have 1,000 francs and I have a interest of 5%, so I'll get, after a year, I'll have 5% of the 1,000 as interest, which is 50 francs. So I have 1 plus my original 1,000, so 1 times the 1,000 plus the 5% plus the 50 as my new amount. So that's why I have 1 plus p%. And in that way, I also see that p%, I can get that just by turning it back as b minus 1. So let's look at two examples. If the growth rate is 7%, then b is 1 plus the 7%. So this means I get 1 plus 7% as 0.07. So I have 1.07. If I have a growth factor of 1.32, what do I have to do to find the growth rate? I have to subtract 1 from the 1.32. So I get 0.32, and I can write that as percent. That's only 32%. In our formula for the exponential growth, we denote the growth factor as b, but in general, we use the notation r with time unit as an index, so for example, r week, r day, or r 3.2 hours. The obvious advantage of this notation is it becomes immediately clear to what time unit this growth factor refers to. Now let us look at some examples. Let's continue with the example 5 that we started before. So what are the a and the b in our growth function? A is 100, the starting amount, the initial amount, and b is the 1.2 per week, the growth factor per week. So our growth function is referring to the number of rabbits. That's just 100 times 1.2 to the power of t, t in weeks, time in weeks. Your turn, try to find the number of rabbits after 2 weeks and 3 days. Stop the film, and here comes the solution. We want to know the f of and t is 2 weeks and 3 days, which means it's 2 plus 3 divided by 7. That's the time. 2 plus 3, 7. Well, that's 17 sevenths in total. So we want to know f of 17 sevenths, and now we can insert that. We get 10 times 1 to the power 1.2 to the power of 17 divided by 7, and using our calculator, we get approximately 155.7 rabbits. Now let us find the growth rate of the number of rabbits per month. And we assume for simplicity that 1 month is just 4 weeks. 1 month is 4 weeks, so we look at the amount of rabbits after 1 month, which means after 4 weeks. And this is the 100 times the 1.2 to the power of 4. And let me just write, instead of the 100, just a, the starting amount, times 1.2 to the power of 4. You'll see in a moment why I like to write it in that way. Well, how many rabbits, by how much has the number of rabbits grown? This means the R of the month is just the number after 4 weeks divided by the original amount, and we see that's the a times 1.2 to the power of 4 divided by a, so we just get 1.2 to the power of 4 as the rate of growth rate per month, and that's approximately 2.07. This means that the number of rabbits is more than double after a month. The growth rate per month, p month percent, let's write something like that, is then just the r months, so 2.07 minus 1, which is 1.07, which means we get 107%. Now it is your turn to try to find the growth rate per day. Stop the film, and here comes the solution. 1 day is 1/7 of a week, so what we're interested in is at the number of rabbits after a 7th of the week, and we get 8 times 1.2 to the power of 1/7. The growth factor per day is then just the number of rabbits after 1 day divided by the original number of rabbits at the beginning, the initial number, so by the a, so what remains is 1.2 to the power of 1/7, which is approximately 1.03, and so we get for the growth rate per day 1.03 minus 1 here, 0.03 or 3%. In example 6, we have a yeast culture that starts to grow exponentially at 8 a.m. We want to know what is the volume. We're given the volume at 10 a.m. and at 1 p.m. And what we want to find is the growth function of this yeast culture, then specifically the volume at 0:30 p.m. and 4:30 p.m. We also want to find out how long does it take for the yeast culture to double its volume, and in the end, what was theoretically the volume at 6 a.m. So counting somehow backwards. So we start with the ansatz, which is just that of exponential growth. So f of t is a times b to the power of t. T is the time in hours since 8 a.m. F of t is the volume of the yeast in cubic centimeters. A is the initial amount or initial volume of the yeast, and B is the growth factor per hour. To be more precise, F of t is the volume of the yeast after t hours. We're given the volumes at 10 a.m. and at 1 p.m. 10 a.m. means 2 hours after the starting time, so this is the f of 2. And that's now, using our ansatz, a times b to the power of t. The t is the 2, so a times b squared. At 1 p.m., that means 5 hours after the start, we have f of 5, that's the yeast volume 5 hours after the start, which is then a times b to the power of 5. And we are given that at 10 a.m. the volume is 20 cubic centimeters, and at 1 p.m. it is 67.5. So what we have here now is an equation system with two unknown, namely the A and the B. Yes, we'll draw this bar for the equation system here, not here. So now how can we calculate that? The simplest way, but for many of you probably puzzling, would be to take this equation and divide it by this one. So when I divide these left-hand sides, what remains is then just b to the power of 3. And here I get a number, so I get b to the power of 3 equals to something. Let us do it in another way. Let's solve first this equation for a. So I get a equals 20 divided by b squared. Let's call that 1 star. And then let's insert that now into the second equation. So we get 20 divided by b squared times b to the power of 5 equals 67.5. Now we can divide by 20 and at the same time cancel out b to the power of 5 by b to the power of 2, which yields b to the power of 3. Let's continue down here on the left hand side. 67.5 divided by 20 is 3.375. And now to find b, what we have to do is just to take the third root. So we get b is the third root of the 3.375, and it turns out that that's exactly 1.5. So what we need also to find now is the a. Let's insert that into 1 star, what we found. So a is 20 divided by 1.5 squared. So approximately 8.9 cubic centimeters. So our growth function is, by inserting our a and b in the ansatz, 8.9 times 1.5 to the power of t. That's f of t. Now we have to provide the volume of the yeast at 3 time points, at 12:30 p.m., at 4:30 p.m., and this theoretical volume at 6 a.m. already in the morning. So at 0:30 p.m., it should say here, sorry, this means that's f of 4.5, because it's 4.5 hours after the start. So we get 8.9 times 1.5 to the power of 4.5, which is approximately 55.2 cubic centimeters. At 4:30 p.m., well, that's f of 4 hours later, so it's 8.5 hours after the start. So 8.9 times 1.5 to the power of 8.5, which is then approximately 271.4 cubic centimeters. The last question is, what is the volume actually at 6 a.m. already before the theoretical start? So, well, the idea is here very simple. We just say we are 2 hours before the start, so we're at time -2. So don't try anything with turning things around, recalculating something. We just say it's f of -2. We go back 2 hours in time before 0. And we get 8.9 times 1.5 to the power of -2, which tells us in the end the theoretic volume then is 4 cubic centimeters. The last question is about the time it takes the volume of the yeast to double. So let us call capital T the doubling time. This expression doubling time is an invention of mine. And let us look at the f of capital T. This means the volume of the yeast at time point capital T. We could now insert this capital T here in the function for the growth, but let us insert it first just in the general growth function. So we get a times b to the power of capital T, and that's equal to the 2a, because we know after time t, capital T, the initial amount a has doubled, so it's 2a. Now we can, looking at this equation, we can divide by a, and we get b to the power of t equals 2. Now let us insert, our b here is the 1.5, so we see 1.5 to the power of t equals 2, and now we can solve that for capital T. We don't know yet how to do it formally, so we'll just use our numsolve function of the calculator, and we get that t is approximately 1.7 hours, which means that every 1.7 hours the yeast doubles its volume. Now let us look at example 7, where we have a sheet of paper and we fold it now 50 times. So we fold it once, then we take the folded paper, we fold it again, and so on. Obviously, after a few foldings, it will become very hard to continue the folding, so it's very theoretical, this idea of folding it 50 times. We could a little bit improve it by cutting the paper when folded instead of just folding it, but even then it would become very difficult. So the question, nevertheless, let's assume we could do it. How high would the resulting tower be? Think about it for a moment, just guessing yourself. What do you think how much it is? You can stop the film, just reflect for a moment. Okay, and now let's see how we can solve that. The idea is, let's first guess how thick one sheet of paper is. Think about it for a moment. How could you find a good guess for that? Maybe you want to stop the film. And here comes the result. One way of estimating the thickness of a sheet of paper is just to say a packet of papers of 500 sheets is approximately 5 centimeters thick. So this means that the thickness of one sheet is approximately 5/100 of the 5 centimeter, which is then just 0.1 millimeters. So now calculate the height of the resulting tower on your own, stop the film, and here comes the result. We start with the ansatz, which is just f of t is a times b to the power of t, since we have an exponential growth. The time t is not a time, the t, but it's the number of foldings, which number of foldings we're at. Then f of t is the height of the tower after t foldings. A is the initial height of the tower. This means before we fold it for the first times, which means it's thickness of one sheet, so the 0.1 millimeters. And B is the growth factor per folding. Each time that we fold the tower, well, it grows by factor 2. The height of the tower, independence of the number t of foldings, can be described as 0.1 times 2 to the power of t in millimeters. And we are interested now in the height of the tower after 50 folding, so f of 50, so we get 0.1 times 2 to the power of 50, which is 1.13 times 10 to the power of 14 millimeters. So to change that into kilometers, we have to reduce the exponent by 6, so we get 1.13 times 10 to the power of 8 kilometers, and that is 113 million kilometers. So that's almost the distance between the Earth and the Sun. I assume that hardly anyone was close with their guess to this result, and this shows what really is exponential growth. What happens when something grows exponentially? It explodes suddenly. You can't follow it anymore, and we have seen this problem with the coronavirus just now, and that's why everybody is so afraid of this exponential growth.